Hello, my name is Sophia Krause-Levy, and today I am going to be discussing the topic of investigating the impact of employing multiple interventions in a CS1 course. This work was conducted by myself and my colleagues at UC San Diego. We as a community have been successful at predicting and identifying students that are at risk of failing courses and dropping out of the computer science major. And now it's time to help them. We all want to help our students, and the earlier we can help them, the better. There have been a number of different proposed interventions with mixed success. What if we take everything known, best practices across the board, and do a mega intervention? This is the approach we took when designing our study. Now, there are three promising angles with the one goal of improving student outcomes. The first angle is presenting content differently. What if we have students complete tasks in a different way? Maybe that will improve their outcomes. The second angle is supporting our students. Maybe if students feel better about their abilities, it will improve their outcomes. And the third angle is teaching students how to learn. Maybe our students don't know how to learn computer science. Maybe if we teach them, it will improve their outcomes. Maybe they're all using the hack it until it works approach. Now, these are the three angles with the one goal of improving student outcomes. Prior results in these areas have been mixed, and we thought that by putting them together, we could get a result. We could positively impact student outcomes. Now that we have discussed the three different angles, I'm going to explain our study design, followed by how we operationalize these angles in our study to try and improve student outcomes. We implemented our study in the footprint of a CS1 course. We had multiple choices for integrating our interventions in this course, but we refused to let our interventions take up more time outside of the course. For this reason, we chose the closed lab section students were required to attend. It had to be there so that we could reach all of them every week for 10 weeks. We hypothesized that this would be enough to help their outcomes. Now, our study ran in the CS1 course, and this course had two parallel sections with two lectures that were both taught by the same instructor. The two sections were broken into 3 lab sections each. From these, we randomly picked 3 of the 6 sections to be a part of the experimental and the control groups of our study. These closed lab sections included 50 students each, took 50 minutes, and the students worked in pairs. The experimental and control groups had separate lab instructors, but the students completed the same lab quizzes each week, and the students were emailed separately with the solutions to their labs as to not cross-contaminate between the experimental and control groups. I'm now going to show you the previous research in these areas and how we implemented different types of interventions in our study. A copy of our graph will remain in the top-hand corner to help us keep track of what we are focusing on. First, we will be discussing presenting content differently. We wanted to try to present content in our lab sections in a different way. We looked around and found a recent promising approach, which we will refer to as Thinkathons. The original Thinkathon was a study implemented in an introductory programming course. Students were invited to 3-hour optional review sessions where they worked through paper exercises. These review sessions were held before the final exam. With the exercises being on paper, it was to help avoid the hack it until it works mentality. This study showed success, but did have selection bias, as students had to choose to opt in and attend these sessions. Our students struggle with the hack it until it works approach, so we thought, why not try and expose all students to this type of approach, whether they like it or not, to see if it can have a broader reach. Our Thinkathon intervention was the largest intervention that we used, spanning weeks 2 to 10 of our closed lab sections. The control group was given original labs that had been used in previous quarters where students wrote programming assignments on the computer. The experimental group was given similar material, but on paper labs. The idea was that students would think on paper instead of coding and move away from the hack it until it works approach. Here are 2 examples of solutions to exercises we had students complete in the experimental lab. On the left-hand side, you can see a matching exercise where we had students look at a piece of code and match it to its corresponding description. On the right-hand side, you can see a while loop where we had students go through the iterations of a while loop and keep track of the variables that were being updated as it looped. Now for support interventions. One area of a support intervention that has been used a lot more recently is growth mindset interventions. Growth mindset is the idea that intelligence is malleable and failure should be seen as an opportunity for growth rather than a sign that students don't belong. These have had mixed results in computer science. Cutts et al. Found that it was beneficial to learning, but there have been several studies that have shown no benefit at all. More recently, a study that was done by Carol Dweck and her colleagues showed that while growth mindset interventions did increase students' interest in computer science, it didn't increase their performance. Another area of support is utility value interventions, helping students see the perceived value of computer science to them and engage them in coursework. These can come from simple values affirmations, and just trying to get students to understand the personal relevance of course material. From these, we came up with 2 support interventions, a growth mindset interventions that students completed where they had to write a letter to a future student about a struggle that they have overcome. Our second intervention was a utility value reflection where we had students explain what they're learning in computer science and how it's personally relevant to them. Now moving on to teaching students how to learn. There has been previous work showing that exam wrappers, which is a post-exam reflective technique designed to improve student study skills, showed no effect on students. This is where students would be given something that was wrapped around their graded exam, where they were asked to potentially reflect on the exam, look at the questions that they got wrong, and answer additional content questions. While this showed no effect for the students, we believe they didn't go far enough and that they could be successful if all students had to do it and people were available to help them. For exam wrappers, in previous studies, students had to pick up their exams and complete it on their own. Another recent area of research is a study that interviewed low and high performing students to try to see what the difference is between how these students studied and learned material. It was found that higher performing students have better exam study strategies. They're better at getting help and getting the help they need before it's too late, and they're better at addressing their confusions, especially post-deadline. So after an assignment is due, higher performing students are much more likely to continue trying to get help with areas that they still had issues with and didn't fully understand or got incorrectly, whereas low performing students would just stop at that point and move on to the next assignment. It was also shown that for procrastination, while it did affect both groups, high performing students, when they procrastinated, wouldn't see the negative effects that low performing students would have. So for our learning interventions, our first learning intervention related to post-deadline behavior. It was given after their midterm exam. We had students pull up their midterm exams and look them over in the closed lab sections. They were supposed to reflect on the score they received, look over the questions they got wrong, and try to understand what skills and concepts they were still struggling with that could have led to that. This was done in lab section so that they would all complete it, and we as instructors were able to help them. Our second learning intervention was exam study strategy. This was given 11 days before their final exam in their second to last lab section. Students were asked to look over topics and areas that they felt they still needed more practice with, and then get that help before the final lab. This was to help them not procrastinate studying, get to resources before they disappeared, so interacting with tutors and TAs that were available and getting help during office hours and other times before there were none left and they were left to their own devices to study. This is the final intervention that we implemented in our study, and now it's time to move on to the questions we were trying to answer. All of these were related to trying to improve student outcomes. Our first question was, can combining multiple interventions significantly increase students' performance? To answer this question, we first collected data on the students in our study. The data we collected included the baseline data of incoming average GPA, major, year in school, race and ethnicity, and gender. Now, for those of you that aren't aware of what GPA is, GPA stands for grade point average, and it represents the average grade a student has received in all of their courses during their time at university. We also collected course data, including final exam grades, overall final grades, and their responses to an end-of-the-course survey students were asked to complete. Our student demographics included URM students, gender, and lower performing students. Lower performing students were students that had an incoming GPA in the lower half of the students in the course. Now, it's important to notice that for gender, we only have the options of male and female. That's because we gathered this data from the university that students entered when they entered university, and at that time, the only options were male or female. So we first looked at WDF rates. WDF stands for withdraw, D, and F. So it's students who withdrew from the course got a D in the course or an F in the course. Now, as you look at this data, you can see the x-axis represents the different groups of students we were looking at. The y-axis represents the percentage of WDF rates, and the blue bar is the control bar, and the orange bar is the experimental bar. It's important to know that lower percentages are better in this case as it represents less WDFs. So here, unfortunately, we saw there was no clear evidence that there was a significant difference between WDF rates for these different groups in the control and experimental sections. While it was inconclusive and there is no clear evidence, there is a lot of suggestive stuff. As you can see, in all cases, the WDF rates are lower in the experimental section, and it may be that we just didn't have enough students involved in this study and our N was too small. Next, we looked at final exam scores. Here, we also saw an inconclusive trend between our experimental and control groups. The x-axis, once again, represents the different groups of students, and the y-axis represents final exam average scores. In this case, higher bars are better. The blue bar represents the control group, and the orange bar represents the experimental group. Now, while this was inconclusive, you can notice that there are some trends between these different groups, with the experimental group performing better in many of the cases. There was one trend in gender for final exam scores. Now, in this case, females scored 7% higher in the experimental group than the control group, whereas males scored 7% lower in the experimental group than the control group, though only the females' difference was statistically significant. Now, it's important to remember that we ran a number of statistical tests here looking for significance, so our single finding could have happened by chance, and further study is needed for this. So we aren't sure. We didn't see anything conclusive showing that it can significantly increase students' performance. Our second question was, what value do students perceive from these interventions? For this, we looked at the results of a post-term survey we had the students fill out that had questions related to lab on it. From this, we found that the control group rated lab more positively overall. Students were shown 3 statements and asked to state their agreement with these statements on a scale from 1 to 5, 1 being strongly disagree and 5 being strongly agree. These statements were, lab helped me solve my programming assignments, lab helped me with my learning, and I enjoyed the lab experience. As I stated, in all cases, the control group rated lab more positively, though only one area had a statistically significant difference. This was, lab helped me solve my programming assignments. This makes sense as labs in the experimental section were done solely on paper, almost solely on paper, whereas the students in the control group completed all of their labs on the computer using programming. Therefore, it's easier for them to see a direct connection to their programming assignments. So once again, we're not sure. Maybe it was inconclusive, and students in the experimental sections did not like the labs as much as the controls. So it's important to remember that interventions often fail. We really hoped we would see a result here, but if you're surprised, you shouldn't be. This has been shown again and again in literature and research about interventions. Now, our threats to validity include several factors, including course composition. Our course is not representative of typical CS1 courses. We had more female students than male students. The majority of our students were not computer science majors, and the majority of our students were junior and sophomore standing rather than freshmen. There could have also been unintentional data flow. As I showed you earlier, while the lab sections were split, the lecture sections were mixed between the control and experimental sections, so there could have been some unintentional data flow. And finally, we hesitate to read too much into our results. As I mentioned, we performed a number of statistical tests, so our results should be taken with a grain of salt. Now, why didn't our interventions obviously help? Well, we already heavily used best practices. Active learning was used through peer instruction with the use of iClickers and in-class discussion. There was pair programming on all of the assignments, and we used the media computation curriculum. We also didn't provide students with a direct connection to grades and outcomes. While we were using these interventions, we didn't tell them the purpose of all of the interventions as the students completed them, which may have helped them have a better understanding and have a broader impact. And we hit everyone with everything. It's possible that not all of the students needed all of these interventions and that didn't benefit them. So there could still be something here. Interventions are an important topic and more replications are needed. And we need to try to see if there are ways of combining interventions effectively. Thank you. This is the end of my talk. If you have any questions or comments, please place them in the comment section below.